Hello, we are back now to look at the implementation of our neural net or backpropagation algorithm. So we are gonna look at the implementation of what we just saw here, a very simple one, and look at some other important concept as well. So we start look at one layer class. Remember, we are gonna be building a class to let's say contain our layers. So in this case, it will be the hidden layer here and here, and the input as well. So the layer will be every layer actually, not only the hidden. Let's say how it is. So you have basically two methods, forward and backward, and this will be implemented by other types of layers. Okay, as I said, the layer basically try to predict based on weights, and later going back and adjusting the weights. Alright, so very basic two methods. Let's start implementing a linear layer, which will have some learning as in the layer. Okay, and it starts with some random weights. Remember, kind of random weights based on some logic. Doesn't really matter this logic here. I think the importance of the whole concept. We start with some random weights, and we have the learning rate, and this would be used on our when you are calculating the new weights based on the, let's say, the derivative or or how bad was our prediction. And then we have the forward here. Remember, we were talking about the dot calculation. So forward is basically going and predict, and the prediction is basically use the weights and the input image, and with some bias. Bias is just data that would help in case of the calculation would be zero, so it's not really important. It just work around to avoid zero matrices. And then after forward, you have to go backward and do some extra calculation and calculating the new weights. So basically, you get the input and you get the gradient output. It's basically this. It's the information about how bad was the prediction that we talked, and you do some extra calculation. That's not important. Again, it's a dot of weights transposed. This is transposed. So I think you can add. And then do some transpose weights now for our input, and some more calculation to do the. And then this is the important part. Here we are calculate the new weights based on the gradient that we received. And this, for that, as part of this calculation, we'll look at the learning rates and the gradient rate that you got. And this learning rate, it is an important concept as well. And this would basically dictate how the size or the rate of our learning. And to understand this a little bit better, and we have this here, learning rate is the step size at each interaction while moving toward a minimum of a loss function. Learning rate cannot be too small and not too big. So if you do too small, you see it will be very slow during our training, because we'll be moving very slow towards our optimal weight, right? And cannot be too big, because then it will be past and they will be never get to the right let's say to the right weight or the good loss. So then you have to, it's basically that. So learning rate, it's telling the size of the step that you are moving towards the optimal weight. Okay, and then next concept, it's the loss function, and there is loads of type of loss function, and depend of your problem you have a different loss calculation. Okay, you're gonna see in the following lecture that the loss calculation will be the, let's say, the addition of 2 cross entropy plus something else. So it will really depend of your problem. So in this case here we are using cross entropy, and we don't need to go into the details. So again, you need to understand each all the losses. So it is important, just you need to be able to calculate how far you are from the optimal result, so how far you are from the right answer. So that's what matters. So the calculation here will be different for each loss function. And another thing that you need to understand, it is the derivative or gradient that you saw before, right? The gradient will just basically give you the direction that you need to go. So you know the distance, then you need to go to see the direction that you need to move in order to go to the right place. For example, here, if you are in the point B and you need to get to this point, here is the optimal weight, you need to know which direction you need to go to the right. But if you are here, you need to know that you need to go to the left. So this gradient would help with that, and here is the calculation. So again, you can read this and get a better understanding about what is being happening here. So again, it's a very small code, and you just need to know that to help you to calculate the weights, and the main information that will be here is the directions. We already saw the learning rate, and now you need to look at the activation function, and in our case we are using ReLU. So this will bring a non-linearity to our neural network. So what its non-linearity means here, it is basically if you don't have this ReLU, we will not be able to generalize our model to, for example, to identify a cat or a dog if the image is very different. So when you are training, you are using a cat, like white cat, and if you give a very different cat, you will not be able to identify all the cats, because it will not be generalized, or it will be too linear. It would be very based on the input that you used during the training. So that's what the activation function does, and it's very simple. ReLU here is very simple. It's just getting if it is if the weight it is above 0, just keep the same. But if it is under 0, it would be 0. So basically, you can see it here on the graph. So here it is 0. Everything that down here will be 0, and every forward will be using the right value, the existing value. It's a very simple concept. And here the implementation. So you can see it is basically a max of 0 of the input. So if it is under 0, you just use 0. Super straightforward. And now you're gonna train our neural network, and you'll be using a data set, and this data set we are trying to identify if a given number what is the number that it would contain in the image. For example, this is the each of this here is one image, and you'll need to predict if it is which number it is on this image. Here loading the dataset is not really interesting for our concept here for learning neural net, and this also is how we are loading our data. Not interesting as well. You can just go and look at the code and learn by yourself. Here it's the important part, which is create our neural network model, or creating our architecture. So here basically we are creating our architecture, and our neural network will contain 1, 2, 3, for 5 layers. However, some layer is just a activation ReLU, so it's not really a learning layer. So we will only have 1, 2, 3 learning layers, and it is basically one hidden layer, and you'll have one input layer and output one. So we start with our input layer. Will contain an input size of our image, so that's our input size, and this layer will output 100 neurons, or and you look at the learning rate for calculate our weights for this layer. And then you have the ReLU, and then another hidden layer with you can see that the output one layer would be the input of subsequent layer. Okay, here for example it would be the input 100 neurons and output 200 neurons, and it would be the amount of the input of the output layer would contain 200 neuron, and the output the number of classes, basically the number of items. In our case here it is 10, right? From 0 to 9 will be 10. So the last layer is always the number of option of your output, and it's basically that's our architecture. And then we have forward that we talked. So we go across all our network that we described here, and you'll be trying to predict with every layer. You'll be forward, and that is the forward step. So you go through every layer and execute forward, and just keep the result of those prediction of every layer, and then you will return all their predictions, and we will have this is the training. So we start from here. Okay, we first go to epochs. This is the number of interactions, and then here we are getting the batch data. So it is just going through each image basically and doing the training for that batch, and this is basically the forward step, but you can see that there is some extra things that you do here, but the training batch, it is here, and the first thing you do is go forward, which we already saw that you go through every layer and you get the layer predictions, and you do some an extra calculation here just to add the input as part of the predictions, and then we calculate the loss. So here it is saying the predictions versus the answer, right? So label, it is for that image you have a number, a name, or in our case a number for that image that you are passing. So we are going to compare the prediction versus the real answer, and then you have the loss, and with this loss we're going to calculate the derivative, which will give us which direction should be moving, and then we return this as a mean loss gradient, and a layer input, which you will see here that those results will be used as an input for backward propagation, which will be used for changing the weights in each layer. Okay, and this backward will basically go backward, right? Propagate backward, and do the back propagation which layer that we have, right? That we already saw. So, and it's basically that: forward, backward. And here validate epochs is just some calculation to visualize how our model is behaving during training. So you can see here it's just to build this diagram here, this chart. So this is not really part of let's say neural net understanding. It's just to keep and see how the neural it's behaving. And that's it. It's basically our implementation. It's very simple, and let's just run it. So here you're gonna go through 30 epochs. So epochs, it's iterations, and you're going to use our neural net with a learning rate of 0.1, and you're gonna train it through our image. You're gonna see this is the X train. So this is the image, this is the label for training, this for image, and the label for validation that you use for validation. So one of the things that probably you have seen, that you have to, when you are in the training process, you have to split our data into training data and validation data. And you just run the training, basically doing what we saw here. We saw these steps, and we will get the result logs, and we plot to see how our model was behaving. So basically this is the loss and this is the validation. We start with very high loss, you see, but as we were moving, we were reducing the loss. So basically we are getting closer to the answer, get close to the answer, until we got very good here, very low loss, and our prediction was almost 100%. We start with bad predicting, then you go closer to 1. It's 100% occurrence. Okay, and then we use that data to evaluate a little bit more. You can see the precision for the label 0, 100%. To the label 1 we got 96%. For the 3, 100 as well. And for the 8 was quite bad, 67%. But to all the others was very good. And we take the random, we get one random test. Let's say take the 0, and we try to predict. We use our model, we try to predict, and you can see we are testing 5, and you were able to predict that what we had on that image was the number 5. Okay, so I hope all that made sense for you guys, and look at the code, trying to understand each step, and try not to get too attached to the math, because all that it is not important when you are building our neural net. Okay, see you next letter.